Hi, it's Jim again, and we are continuing on with forces, Chapter 2 in Forces. So we're going to be talking about free body diagrams. They're also called force diagrams. I might use both those terms. I mean the same thing. So if you haven't done the readings yet, please do so. It's chapters 4 and 5 in CLEDA. If you're in Physics 111s, it will be chapters 4 and 5 in OpenStax, and also chapters 5 and 6 in OpenStax. Okay? So when I talk about force diagrams, what we're going to be doing is creating a diagram on the interaction of forces, okay? And again, a force is, we've defined it before, it's just simply a push or a pull, right? And the interactions of those two things are when essentially you have two objects, in this case a kid, a boy, and a wall. You could see that the boy is touching the wall, so that is an interaction of those two things. And so at this point we'd do a force diagram, and we'd probably be doing a free body diagram on the boy. Okay, well, we'll get into that. But basically we have to define terms. A force is simply a push or a pull. And interaction means there is two objects either physically touching each other or working on each other from a distance. Okay. Now, a force is simply something that could change an object's current state of motion or its velocity, but it doesn't necessarily have to change its velocity or its current state of motion, but it can be that. And that also there's this concept of net force, and it'll be the sum of all the force vectors in one direction, like the x direction, and then the sum of the force vectors in the y direction. They could sum to be zero, which means there would be no change to an object's current state of motion. If they sum to be zero, if you're summing up forces, I'm going to mark up this document. If you're summing up forces, basically you're applying Newton's second law. So you sum up all the forces, and then you're going to be setting it equal to mass times acceleration. So this is also called applying Newton's second law. Right? So if you summed up all the force vectors, so here you have an object, you have a positive force of positive 2 newtons to the right, and then a positive negative 2 newtons to the left, a force to the left of 2 newtons. You sum up those forces in the x direction. You go positive 2 newtons to the right, negative 2 newtons to the left, and let's say this is a 1 kilogram object, and you set it equal to mass times acceleration. That would mean 1 kilogram times the acceleration. This will be 0 newtons divided by 1 kilogram, which will be equal to the acceleration, which is equal to 0 meters per second squared, which means there is no acceleration vector on this object. It could have been moving. Maybe it was moving at the time that these forces are acting on it. It would still have a velocity vector on it. Or it could not be moving, right? If it wasn't moving, it would have a velocity of 0 and an acceleration of 0. That means it's just not moving and it stays still. But here, it could be moving at a constant velocity. So this is kind of what we're talking about. Just because you have forces acting on an object doesn't mean that the object is going to be accelerating, right? When you sum up forces, sometimes when you sum those up, they cancel each other out, kind of like the spring problem in the last case, right? When you sum up that spring scale problem with the two 5 Newton forces working down on it, it summed up to 0, right? So the 5 Newton, it was plus 5 newtons, minus 5 newtons, and it was a 1 kilogram spring scale. Right? Well, that summed up to be 0, which means the object wasn't accelerating. So if the object was not moving at the time, then it would continue to not move. But if it was moving at the time, it would be moving at a constant velocity. So I guess this slide here is to say, if forces sum up to be 0, sum of forces equals 0, all that means is that it could be moving at a constant velocity or not moving. for sure, both of those are coming from the fact that it is not accelerating, right? Which is what we're seeing here. Okay. Now, earlier when we were talking about terminology, we had forces and we had interactions, right? Well, there really are only two types of forces that we're really going to talk about in this class. One is called a contact force, right? And that means the two objects that are interacting with each other have to be in physical contact with each other, right? So in this class, that could be just a hand touching a wall or a hand touching a block. It could be just a force of a push or a pull. A spring is another type of contact force. Friction is another type of contact force. There's going to be this thing called a normal, which we'll define in the next activity. We'll talk about that, but that's just a force of a surface acting on an object. And then there's also a rope or a spring, which is a tension force. So all of these are different types of contact forces where an object has to be touching the ground, in which case it'll have friction and a normal force on it, or an object has to be touching a spring, or a rope has to be attached to it. Those all are physical contact forces. Well, there are non-contact forces, right? There are two objects that aren't physically touching each other, but they are working on each other at a distance, right? So one of them is gravity, right? So gravity, if you jump off of a high dive and you're falling towards the water, the earth is going to be pulling you down. So this is the force of the earth on you. And then you will actually be pulling the earth upwards, right? So this is the force of you working on the earth, right? So you are not in physical contact with the earth when you're falling in the air. And so that is the force of gravity. Well, the same thing would happen on the moon too, right? You don't necessarily have to have the air. If you were on the moon and you jumped off the little moon lander and landed on the ground while you were above the moon, you would be falling down. So the moon would be pulling you down, and you would be pulling the moon up, and you're in a vacuum, so you'd be falling. So that's the force of gravity, right? Or the force of whatever celestial body you're standing on pulling on you. Well, that's a non-contact force. Okay. Well, magnetism works that same way, right? If you have a north pole of a magnet close to another magnet, right? Magnets, you have two magnets close to each other. Well, they're going to attract or repel no matter what the distance is, right? So if they're in close distance, I should say, to each other, well, you'll see them actually start to roll towards each other if you have two little rounded magnets, right? So you'll see them actually pull on each other even though they are not in physical contact with each other. Also, electric force, right? You've probably seen things about positives and negatives. Like if you have a positive and negative proton and electron a distance away from each other and you let them go, well, they're going to attract each other even though they're not in physical contact with each other. And same thing, if you have a positive and a positive or a negative and a negative, if you have unlike charges, well, if you have like charges, they're going to repel. Positive and positive, negative, negative are like charges. Well, they're going to repel each other even though they're not in physical contact with each other. Well, the only one we're going to be worried about is not electric force and it's not magnetic force. It's only the gravitational force, which is the weight of the object. So, and most likely we're going to be doing most problems where we're dealing with the earth pulling on the object. So it's going to be just mass times gravity, or the mass of the object times 9.8 meters per second squared. Okay? So when we do these force diagrams or free body diagrams, we're going to be talking about the non-contact force due to mg, and then what I'll ask is what objects are physically touching it, and then we'll define them as push or pull, spring, friction, normal force, or tension. Okay? Well, let's do a problem, and let's just get you ready to doing force diagrams, okay? So you have a person pushing a crate, okay? So we're going to do free body diagrams on both the person and the crate here, right? And don't forget that both people are touching the ground, okay? So what I want you to do is I want you to consider all the forces working on the person and all the forces working on the crate. And I want you to list all of the objects that are physically touching the person and all the objects physically touching the crate. So I just want to point out too that if we talk about the force of the weight of the person, which is the earth person pulling on each other, that is different from the surface of the earth pushing on the person, okay? All right. Well, let's list out what is physically in touch with the person. What is actually the person has a weight, so this is the mass of the person. So I'm going to do mass of the person. I'm going to subscript it times gravity, because the earth is going to always be pulling an object down towards the bottom of the page. The crate is touching the person. And then what else is touching the person other than the crate? All right, well, the ground too. So we'll just call that the surface for right now. So the surface is touching the person. Over here, you have the crate also has a weight to it, right? So it'll be mass of the crate times gravity. So that's the non-contact force. Now that we've defined the non-contact force, what is physically touching the crate? Well, it's gonna be the person, and then also the crate is sitting on the ground, so it's the surface, right? So we've kind of listed out what forces are acting on the object, right? Some people may say air, right? But if you removed all the air from the room that you're sitting in right now, nothing would really happen to you. You would still be sitting in your chair, but you'd probably need to find a way to breathe. And so air is not going to be a force that is working on the person nor the crate. That's not going to influence their motion or anything like that. Okay? Well, we're going to take those lists and we're going to actually turn it into a force interaction system, right? So the surface of the ground is going to actually produce two types of forces. Well, really, it's going to produce a force holding this person up, right? So this person, the surface of the ground is going to be holding you up, right? It's going to be applying a force to you, right? Upwards. Because if the surface disappeared and you just deleted this person would begin to fall. So something was holding them up. Right? Well, the earth is also pulling, so this is the force of the surface. It's also called a normal force. And we'll get more into it in a little bit, but a surface is going to apply this thing called a normal force. And what they mean is this normal force that is working on the person. I'm going to erase this N and thicken this right here. This normal force. So the ground is pushing up on this person. And if you notice, and this is called the normal force, that this force, what you'll find out, is always perpendicular to the surface, right? So if the surface was tilted like this, and the person's foot was right here, foot, the normal force would be acting out in this direction. Right? So that's the surface right there. But the surface is also going to apply another thing, which is a frictional force. So surfaces apply two forces. One that is perpendicular to the surface, and another one that is parallel to the surface. And that's a frictional force, right? So if you are pushing against a crate, you would feel your feet skidding backwards right here. So this foot would actually be moving backwards. Well, what it seems to be is that the frictional force is almost always the opposite direction of the velocity vector, right? So if your foot is moving backwards that way, the frictional force is what's pushing you to the right. And so this would be a static or kinetic friction force, and we'll worry about that later. But so this person is, so a surface is going to have two forces on it. Well, this is going to be the same for the box, right? The box is going to have a normal force up, and it's also going to be working against this person, right? If this box isn't moving, it's because its friction is actually working against it, right? It would want to move to the right, or if it were to slip, it would want to slip to the right, but that means its frictional force is opposite direction of the velocity vector, which will be to the left. Okay? So that's why in this interaction thing, they have a normal force and they have a friction force. They have the surface, which is this S, and they have a frictional force and a normal force tied to that. But they also have gravity tied to it as well. And so they call that the entire Earth, right? And so this will be the weight of the person times gravity. And this is going to be the weight of the crate times gravity. Okay? And then finally you have the pushing. And this is the force interaction between the person and the crate. The person pushes on the crate pushes back on the person. Okay? Well, that's leading us up to force diagrams. So let's go back to this. To do a force diagram, what you have to do is you have to pick out the center of mass of an object, right? I'm going to erase all this. Okay, and since I have my forces listed, we'll just use this instead of that force interaction stuff. So I'm going to pick out the center of mass of a person, and that's right actually about the navel area, which is weird. And the center of mass of this object is probably right here. So now what you're supposed to do is a proper force diagram. You have to draw the coordinate system for each one of these things. Okay. All right. So let's draw a coordinate system, and I like to use red, and so each object is going to get its own force diagram, its own coordinate system. And I use a dotted line for that coordinate system. So positive x is to the right, negative x is to the left, positive y is up, negative y is down. And you're going to do the same thing for the other object too. Normally you don't do a force diagram for multiple objects, you just do it for one object. But that's what this problem is asking. So this guy's coordinate system is going to be positive x to the right, negative x to the left, negative y is down, positive y is up. I usually try to keep the coordinate systems comparable to each other, right? So the y direction should be parallel to the y direction of both objects, right? You want to keep both objects, if you have the chance, having the same coordinate system, right? All right. Now what you're going to do is you're going to create vectors, okay? So I am going to go back to black, and let's create a vector. So again, that surface is going to be working on the person, and you're going to draw a vector for the surface of an object. So I'm going to use the surface as blue. Why did that turn to? So I'm going to grab this. So actually, let's do mass times gravity first. All right. So I grabbed a vector, and that for some reason is pink. I'm going to use blue for that vector. And so now I'm going to label it. So this is mass of the person, is pointing down, so it's in the negative direction. And I should have it being blue. So it's negative down, and it's mass of the person. And I'm going to subscript it P times gravity. So that is this vector right here. And that's the weight of the person, right? And I'm going to make it a smaller vector because I want to make the person have a smaller mass than the object, than the crate. All right, now the crate is going to have a vector down as well, but it's going to be a big vector. I'm going to bring it over here, and I'm going to actually just use that as my label, but I'm going to subscript it with a C. So I double clicked on it and get to here. So that's mass of the crate times gravity. So a longer force vector. So notice I'm attaching it, both of these vectors to the center of mass. And so notice that the mass of the crate is much longer than the mass of the Earth. Mass of the crate is much bigger than the mass of the person. So it's going to have a longer force vector. Since gravity is just 9.8, it's going to be proportionally longer. Okay? So I just did the non-contact force, both of these. And both of that. So that's good. Now let's talk about the person working on the crate, the force of the person working on the crate and the crate working on the person. I'm going to use black for that. Now, the crate is going to feel the person pushing him to the right, pushing it to the right. So this will be the force of the person on the crate. And I'm going to subscript that. And I'm going to make that black. And I'm going to put a plus there. A lot of professors don't put directions on their free body diagrams. I do. Since you've defined your coordinate system, you might as well then attach a plus and a minus to your force vectors. Okay. So now I'm going to copy these two things and just attach them to the object over here. And so, since the person's pushing on the crate's going to push on the person and equal and opposite amounts. So now, that person is going to feel the crate pushing him to the left. And it's the crate acting on the person. Okay? All right. Now we have to do this, since we've done that force pair, we'll go ahead and take that part off. And now we have to do the surface. Now the surface is going to be creating two things. A normal force on both objects, the ground holding it up, and also a frictional force, which is like a weird F, like a cursive F. But let's do the normal force. Well, just for right now, the ground is going to be holding up exactly the weight of the person in this particular case. Okay? And I'm going to call that, I'll use orange for that. So the normal force is, again, going to be equal to, in this case, it's going to be equal to the weight vector, right? Unless the person's accelerating up or down, that force is going to be equal. So this is going to be the normal force, and it'll be upwards due to the person. So that part is going to be subscripted, and this whole thing is going to be orange. Okay, cool. Now I'm going to select both of those, and I'm going to do the crate. Since the crate has a bigger weight vector, the ground is going to have to hold up more weight, which otherwise it would sink into the ground. So it's going to hold up exactly its weight, and this is going to be the normal force on the crate. Okay, now there's a frictional force working on this, right? This person's foot is going to want to slip to the right, so the frictional force, which I'm going to use as red. Should I use red? I'll use red. Actually, let's use green. The frictional force, and we'll worry about the components of friction. Is going to be, we talked about that earlier, so the frictional force is going to be working on this person to the left, right? Correct? So the person's foot is going to be sliding to the left, so the friction will be to the right. And this, we're going to now call the frictional force. And as long as the person isn't moving, oh boy. And this is the friction, and this is the static friction. I'm saying the person is not moving of the person here. Okay. All right. So here's the static friction of the person, and the crate is also going to have a frictional force on it, opposite that its direction as well. So it's going to have a friction working on it to the left, which is going to then be negative. And this friction, even if it's positive and you know it's positive, still put the plus in there. Okay? So you're going to get a force diagram that looks something like this. You have 4 arrows pointing in basically the cardinal directions, right? Which is how they got this, right? So the person has normal force holding, the ground is holding the person up. The friction of the person is actually pushing the person to the right. They have a weight down, and they have the crate working on the person to the left. Okay, and this is the same thing that we just drew, just different subscripts. Normal force is up on the crate is down, the person's working on the crate to the right, the friction of the crate is working to the left. So this is the basics of creating a force diagram. Okay, all right, and so again, the steps of this is you make a list of all the forces acting on all the objects, right? And in here, what they did is they did what is called an interaction diagram. I think it's fine just to list this out, and it might even be better to list this out and actually give it directions too. Just go like, this is down, this would be to the left, and this would be up, and then up, and then this would be to the right. And do this for the other object too. This will be up, this will be left, and the person working on the crate will be to the right, and this will be down. And then once you have that list made, go ahead and do a little dot for the center of mass of each object, draw your coordinate system, okay, and then basically attach those forces with vectors and try to make them proportional to what you imagine the force should be. In here, I made my crate have a large force vector down, meaning the crate was heavier than the person, right? So they never, it doesn't look like they didn't say that the person in the crate had the same weight. It looks like this crate has a lot more matter on it than the person, so that's why I was considering the mass of it greater. Mass times gravity, rather, greater. Okay? So that's the basics of it. And so this is kind of like another example of a force diagram. You could go through this if you'd like. They're just basically talking about you have two people here that are pulling on a crate in equal amount, right? So the person's pulling on the crate. This crate is pulling on this person, the green person. The red person's pulling on the crate's pulling on the red person. So now you're doing a force diagram just on the crate. The crate is probably going to have a normal force up, and it's got a weight vector down, mass of the crate times gravity, and that's down, right? So they're neglecting the y direction stuff. I think they're only considering the x direction. And then they're going to be leading into equations, okay? Well, actually, they're basically just looking at this and saying, well, if the person here is pulling more to the right than this person is pulling to the left, well, then that means there's going to be a net force to the right, which means there'll be, since net force is the sum of forces, you sum them and set them equal to mass times acceleration. So if you have a net force to the right, if this is greater than this, then you will have a positive net force, which means your acceleration will be to the right, which means it'll be speeding up as it's moving to the right. Or, well, actually, it'll just be accelerating to the right. All right. I hope you enjoyed this. This is just the basics of doing a free body diagram and force diagram. Okay? Bye.